All right, the next review problem is one out of your book. This is number 41, chapter 7. So it's kind of an interesting situation. You have a slope, you have a physics book on top of the slope, and it's connected by a string to a coffee cup hanging down here. Now the coffee cup is 500 grams or 0.5 kilograms. The physics book is 1 kilogram. We know the slope is 20 degrees, and there's friction. We have static friction and kinetic friction between the book and the inclined plane. But what happens is, like usually we don't start this way. Usually we start and we see what happens. But somebody's going to give the physics book a push up. So it has an initial velocity going up the inclined plane. We want to know then, part A, how far does the book slide up the thing before it stops? And then when it gets to the top part, does it slide back down or does it stay there? Alright, so we start this problem the way we start every single one of our force problems. We do free body diagrams. So we got a free body diagram for the physics book, where we have gravity, mass of the book, times g. We have a normal force going this way. We got tension going this way. We got friction going this way because the book has an initial velocity up the hill. That is it. That's all we have. So we do our coordinate system, and we have to break up gravity, so we have mb g cosine theta. Remember, this is our angle theta. And we have mbg sine theta going this way. All right, let's do the coffee cup. It has the mass of the coffee cup times gravity, and it has tension. That's all it has. All right, we have to be consistent again. I'm going to say that this direction is positive, which means that this way is positive. So we're consistent here. Okay? All right. That's all we need. So now we do F net x. Let's do F net x for this one. Well, F net x is going to be equal to minus t minus the friction force minus mbg sine of theta, which in our case is not 30, it's 20 degrees. Okay? Notice all those are going down. But this is accelerating, so we're going to replace this with mass of the book times its acceleration is minus t minus the friction force. And let's replace that with mu sub k times the normal force minus mbg sine of 20. Now to get the normal force, we have to do F net y. So F net y, we have the normal force minus mbg cosine of 20. That's equal to 0 because it's not flying off of the inclined plane, so we can say the normal force is equal to mbg cosine 20. Okay. Now I can plug that back into here, and I get that MBA, so I'm going to plug this back into here. It's going to be equal to negative t minus mu sub k times MBG cosine 20 minus MBG sine of 20. All right. We can't solve that because we don't know what t is. And so to figure out what t is, we're going to have to go to this one. So we're going to do the coffee cup. So this was the physics book. Let's do the coffee cup. We're going to do F net x in this case. Positive is going up, so we got t minus mcg. And this becomes mca because the coffee cup is accelerating as well. They're both accelerating. Okay? Solve it for t. Essentially, I'm just going to move that over there and say as t is equal to mca plus mcg. Now plug this back into here. When I plug that back into there, what I end up with is MBA is equal to, and notice this is negative, so I have to distribute the negative, minus MCA minus MCG minus mu sub k MBG cosine 20 minus MBG sine of 20. And I may be off of the camera. Okay, I'm running out of room, so what I'm going to do is you have all this now, I hope. I'm going to move over here. Leave the free body diagrams. So we're going to move all this up to here, but I need to get the A's by on the same side. So I'm going to move that over to this side and then rewrite the whole thing over here. So I'm going to end up with MBA plus MCA is equal to. So I just move this over to that side. The equals now here. So now I have minus MCG minus mu sub k MBG cosine of 20 minus MBG sine of 20. All right, now we pull the A out and then we divide by that. So we're going to get that A is equal to negative MCG minus mu sub k MBG cosine 20 minus MBG sine of 20, all divided by MB plus MC. Now I can plug in all my values. So this is minus 0.5 times 9.8 minus 0.2 times the mass of the book, which was 1 times 9.8 times the cosine of 20 minus 1 times 9.8 times the sine of 20. All over 1 plus a half. You plug all that into your calculator, and you get that the acceleration is minus 6.7 meters per second squared. And as we figured out, it has to be minus because it should be going down the slope. All of the forces are going down the slope. But it didn't ask for the acceleration. It asked for how far up it goes. So how far up it goes, we're going to use our regular equation here, the ones we've been using a lot, plus 2a x minus x naught, our constant acceleration equation. All right. So to do that, we know that the velocity at the top is going to be 0. So we're going to get 0 is equal to, and the initial velocity was given was 3. Pretty sure. Make sure. Was 3 meters per second squared. So it's 3 squared plus 2 times negative 6.7 times x. We're just going to solve that for x. So this becomes negative 3 squared over negative 2 times 6.7. If I move the negative to the outside, it's all equal to x. You get x is equal to 0.67 meters. So that's how far it slides up. All right. Now, the second question is, when it gets to that top part, so the book's up here, it's slid up to here, still connected to the coffee cup. All right. Will it slide back down? If it's going to slide back down, it's going to change our free body diagram. So we're going to do a new free body diagram. What changes on this free body diagram for the physics book? Well, the normal force and gravity don't change. The only thing that changes is this. The friction force now goes the opposite direction. And when it gets to that point at the top, it stops. And so it becomes static friction. And the only way to overcome that, to see if it moves, is we got to have more forces going down than we have going up. So the forces going down is tension plus MBG sine of 20. Okay. If that's greater than the static friction force, then it'll move back down. If it's not, it'll just stay there. Okay? Well, the static friction force is mu sub s times the normal force, but the normal force is mb g cosine theta. Okay, we have all this, right? The static coefficient of friction I gave you was 0.5. So this is 0.5 times 1 times 9.8 times the cosine of 20. This side, the tension at maximum will be the tension if it's not moving. Remember, if they're accelerating together, then that tension will decrease. But so the maximum tension will be right when it stops. So at that point when it stops, the tension is just equal to mcg. So mcg plus mbg sine 20 are the forces trying to make it move back down. Well, this is 0.5 times 9.8 plus 1 times 9.8 times the sine of 20. And we have to see which of those is larger. So if we calculate those out, we get that this side is equal to 8.25 newtons. And this side is equal to 4.6 newtons. Since this is greater than this, yes, it'll move back down the slope. So it'll slide up and go there, and then it'll start sliding back down, and it's going to accelerate back down. It's going to accelerate at a lot smaller rate than it's accelerated going up, because friction is flipped around, and you would have to switch it to kinetic friction. But that's all they asked for, so what you would say is it slides back down.